Okay, so first, let me title this Practice Problems. All right, so I said that we had two sets, a set A that has John, Peter, and Paul, and a set B, let me write it down here. This is John, Game of Thrones, John, Tiger King, Peter, Westworld, and Paul, Journey to the West. Okay, so the first question was, is A a subset of B? No, A is not a subset of B. So a pretty straightforward way to know this is that B is a set with 4 elements, or 4 tuples, or 4 vectors. Each of these are of dimension 2, and A is a set of size 3, so it has 3 elements, or 3 tuples, or 3 rows. All these are equivalent words for this. And the dimensions are different. So these are of dimension 1, these are of dimension 2. So right off the bat, A is not a subset of B. Another example would be if you had a set C equal to, let's say, John and Carrie. Well, here C is also not a subset because Carrie doesn't exist in A. But if C were just the element John, then C would be a subset of A. So same dimensions, and also every element that appears in C also appears in A. So that one was pretty straightforward. This is being recorded, yes. So I started recording as soon as I started going over these practice problems. So the next, what is the intersection between A and B? And I'm trying to use these symbols here just to sort of remind you what they mean. Here, the intersection between A and B is this symbol. This is read as the empty set. This is the same thing as writing this. So curly brackets with nothing inside of them. It's usually written, it looks like a 0 with a big cross through it. That's the empty set. 3, what is the union between A and B? So, yeah, actually this question was not very well motivated. Because without saying anything else, if these were sets, then the union would be John, Peter, Paul, and each of these. So you'd have this one, you'd have this tuple, you'd have this tuple, and this tuple. This is the way that it would work with sets. The dimensions don't matter. But for relational algebra, these do have to be the same dimensions of the same kind. So this answer is actually also the empty set. This is true for sets, not for relations. So on any homeworks or on our final or something, know that we're working with relations, and I'll do my best to avoid any ambiguity of this kind. That being said, if there is ambiguity that is never cleared up, I'll go with what works out best for the students. But do ask if something isn't clear. All right, so let me get rid of this. Okay. I'm going to move this to make it cleaner. Cool. All right, 4. What would be the relational algebra expression to get the names of all the shows in B? So, what relational algebra expression results in the names of the shows? I'll put it here. I have enough room. Okay. So this is just a simple projection. So projection, keep second coordinate of B. You could just write it this way. So I'll remind you that a projection takes in a relation and only retains certain coordinates of each tuple. So here, this projection, we're saying it will take the set and return only the second coordinate of that set. So that one's just a pretty straightforward application of a projection. Sigma second coordinate, so sigma is a select. A sigma will pick out certain tuples. So maybe I only want these 2 tuples, but it doesn't take coordinates from the tuples. Where when I say coordinate, this is one coordinate and this is another coordinate. So the number of dimensions of the vector is equal to the number of coordinates in the row. Again, these are just different vocabularies that say the same thing. So, all right. And the last question, I think I only need, let's see, can I go down this way? Haha, found out a new way to do it. Okay. So the last question is how to get just the names of the shows John likes. Okay, so sort of the way to think about this is that um, there's a couple of things that you want to do. First of all, this B, this set, assuming that this is name and the show that they like. Wait. So projection only selects coordinates, such as first or second, for example. Yes, that's right. So a projection, I hesitate to use the word select. It filters coordinates. I don't want to say select because I don't want to mix it up with the actual select operation. Yeah. So a projection takes, you can think about it like it takes something with many rows and it returns something with fewer rows. So maybe just the first two rows, for example. Excuse me, columns. So a projection filters out columns. A select, you can think about it as filtering out rows from a table. And so if you have a big table and the table has rows, and in addition to that, the table has columns, then by combining a select and project, then you can do things like pick out individual cells, if you like, of the table. So the project will work on these. That's pi. And the sigma, the select, will work on the rows. Are you going to post your lectures to Blackboard? You mean the like these OneNote things? I could export them to a PDF. Sure. I guess I'd prefer to do that when it's finished, but maybe I can. Yeah, I'll start to roll out some of these. Is that your question? Uh, yes. Okay. Sure. Okay. So for this, um, uh, first we can select the tuples that we care about, and so that will be a select. And I'll say name equals John. So we'll be just selecting those tuples of B. And so after that, we'll have this set here, just John. But we only care about the shows, so keep second coordinate of this select. And the result of that will be keeping just the second coordinate, so just the names. Why is 3 an empty set if it's a union? Right. So again, this is the way that these work. A union and an intersection. Well, at least the union, it works slightly differently with sets and with relations. So it might make more sense if I make it kind of like a table, which is a very good way to think about relations, is just tables. Oh, come on. Okay, let me get some more room here. So if I have a table here with name and I don't know, address. Um, well, no, here. I'll do name and show. Name and show. then this has 4 rows here. So you have John, Game of Thrones, you have John, whatever, Peter, whatever, Paul, whatever. And then you have another table here, just name. And this has 1, 2, 3 rows. How would you combine these together? I mean, you could try to put the name here, but then if this is, John, Peter, and Paul, do these go in the first 3 rows? Is this a null? It's just sort of not clear. So these need to be of the same types for relations. So the way that a union works for sets and a way that it works for relations is slightly different. What you would need to do is to get something with 3 coordinates in order to have this union sort of work, I guess. So, yeah, this is just the way it works. Well, A also contains tuples. I'm just not making that explicit. So these are also tuples. I'm just not writing them that way. Right. So the way that a union actually works is here. If you have a table here, A, and you have another table here, B, the way that these would be, if you make a union of A and B, what you would get is a table A union B that looks like this, where A would be here and B would be here. Right? And so that works because their dimensions or the coordinates that they have are the same. But because here A has a 1 coordinate name and B has a coordinate name and a coordinate show, I mean, you can't add on to the table in this way because there's sort of this missing area here. And so that sort of doesn't compute. Okay, so the way that the union's actually going to work is by extending the table in this way. Does that make sense? Okay. Great. All right. I will try to put together some more questions for the beginning of next class as well, if people still find that helpful. And yeah. Okay. Let me check. Okay. So let's move on with today's lecture. Okay. So the last class, I spent some time talking about sets. Although really what we're concerned about are relations. In fact, because we're talking about relational algebra. So this is the algebra between relations. And as we discussed before, a relation is here. A relation is something that looks like this. It has a schema, which is a collection of named attributes and their types, along with an instance, which are sort of the values for those. Okay, so the relational algebra is how to perform functions on these tables in order to create new tables or new relations. Okay, so I'll try to speak more about using the word relation and less the word set, because as we just saw with the union, the result is different. You can take two sets of different dimensions and you can union them together, but that doesn't work with relations. So we talked about some sort of notational things. We have these vertical brackets to denote the size of a relation. Here, the size would be the number of rows of the table, or the number of tuples in the relation. We also have these two notations for being a subset or a strict subset. We have the notion of disjointness. That is when two relations share no rows in common. We have the notion of a complement. So this would be, for example, if you had a relation, I don't know, attribute 1, attribute 2, attribute 3. And if you select maybe this part of the relation, then its complement would be everything outside of that. And this will be a useful notion later. I'm not sure if we'll get to this today with the examples that I'm going through, but this is something that is required for some examples that we'll go through. All right. Then we started to go through the different functions in relational algebra. Each of these are fairly straightforward. You have the union. Maybe I'll try to draw something over here. I don't know if I want to mess up this or not. But yeah, the union here would be if you have A and you have B, then A union B would look like this, where you have A and B for relations. You just are sort of concatenating the tables row-wise, not column-wise. Okay, you have an intersection. So that would be which rows they have in common. It could be sort of a finer granularity than that, but in any case, it finds those parts of these relations that are shared between two relations. That's an intersection. And the set difference is taking all of those elements that are in one relation that do not appear in another relation. Okay, I won't draw these table diagrams for all of them, but maybe it's sort of helpful for the union. Okay, these three functions are unique in the operations of relational algebra, in that they work on the same kind of tuple. And so what I mean by that is illustrated in this example. You would need, if A and B have, here they would need to have the same schema. So that's what I mean by the same kind of tuple. Looking back at the relations, this part needs to be the same. If you have one relation like this, if you wanted to union this with another relation, then that relation as well would need the same kind of schema in order for this operation to complete. And the result would be another relation with maybe more rows, but with the same schema. Where am I here? The same kind of tuple, i.e. the same schema. Okay, so when you do an intersection, it will be the same thing. Both of the two relations need to have the same type of schema in order to find out which rows they share in common, or otherwise how to keep the rest. I mean, if you're taking out those parts of A, or those parts of B that also appear in A, then it means that those parts would have to be of the same type as B in order to remove them. So A and B would have to share the same type of schema. Okay, so these three operations have that commonality. The schemas between any relations being acted on should all be identical. For the rest of these operations, you are coming up with a different schema. So if you have a cross product, where our cross product is again taking all pairwise combinations. So the cross product, if you have something A and something B, then the cross product of them is going to look like this, A and B. Well, not actually, it will be longer than this. The table will actually be longer in the vertical direction because of the pairwise combinations, but this diagram isn't quite accurate, but it captures this part of it, that this will generate a new schema here, where this is the schema of A schema, and this is B schema. That's the more accurate thing to say. But the length of this will probably be longer because of the all pairwise combinations. You know, if A has 10 elements and B has 10 elements, then this table will have 100 elements. So this would be 100 long. If this is 10 long and this is 10 long, then this table would be 100 long. And if this has 2 columns and this has 3 columns, then this here would have 6 columns. Okay. So let me erase these. I'll leave the rest because that's accurate. Okay. Any questions so far? Everybody following? Am I moving too quickly, too slowly? All good. Okay. Then, the projection. As I said, this does a filter of the rows, or of the columns. Excuse me. So this would take a table, let's say A, with 3 columns and by applying pi, you might get something with maybe just the last two columns. So this is the way that the projection works, and the select outputs a subset of whether to keep the tuple or not. So that's whether to keep the row or not. So here, if you have A, and this has 1, 2, 3, 4, 5, let's make it 6 rows, then by applying the sigma, you might get a table that only keeps 3 of those, only keeps half. All right, so sigma operates on the rows, projection operates on the columns. Clarify, does that mean cross products can have different dimension sizes? Yes, it can. That is correct. Okay. Rename is pretty straightforward. Here, if you have a table A, B, C, and you apply row, this is pronounced row, then the result might be a table alpha, beta, gamma, whatever. So renaming the columns. You can do this whenever you want, but there's a reason why you need this to exist. And that will go into the last operation that I haven't talked about, called the natural join. And this is denoted with this symbol. I think it's just a bow tie. But before I go into the natural join, any questions about the other operations? No. Okay, good. All right. Then the natural join. This, where's my pen? Here. The natural join selects or filters tuples with a common attribute. So this is maybe easiest to understand pictorially. Let's say here I have a table A, name, age, and we have John and Peter. And John is 18, Peter is 17. And you have a table B, name, I don't know, what's something that doesn't take up very much space to write. OS. So John, Paul. John uses Mac OS, and Paul uses Linux. Then A cross B would result in name, age, OS, and this would just have a single element, John, who's 18, who uses a Mac. Okay, so what's going on here? Let me see if I can write this more explicitly. And the natural join is something that you actually don't need. I will give examples where that use it. I'll try to give as well when it's not, or the alternative way of using it. But I will ask for you to try to avoid the natural join. It seems like something that could make your life easier, but it can lead to some mistakes that are hard to catch because of sort of the assumptions that are being made. So really, this is equivalent to doing a cross product rename. Well, I won't get to the rename part. It's similar to doing a cross product plus select. Okay, so what's happening is first you would take a cross product between these two tables, and you'd get one that has it would be like gluing these two tables together this way, and then finding those rows that have the name column the same. So here John is equal to John, so it passes the filter. Here Peter is not equal to Paul, so this does not pass the filter. After that, you throw out one of the name columns, and you keep what is remaining in this table, which here would be this table. So it's joining both of these tables together and creating a bigger table that shares the attributes from table A and the attributes from table B, except for the one attribute which they have the same named portion of it, and it only keeps one of those. So here this only has one name column. All right, let me erase this because I don't want this to get really messy. I'll keep that much though. So kind of like a Cartesian join where the name keys are the same in each table. Right. So this would be the key is the attribute that you're joining them on, and yeah, that's right. The name and the keys are the same. Yeah. So we'll see more examples of this, but this is sort of the reason why the natural join is kind of redundant. In fact, you can reproduce it by using the cross product, select, and also the rename. And this is the reason why the rename is necessary. But it's not clear from this example why you need a rename. So I'm taking that part out, and I'm just saying that this is approximately equal to the cross product and the select. So the cross product ends up sort of gluing two tables together row-wise, or column-wise, excuse me. And then the select is the thing where some rows are kept, like this first row, and then other rows are filtered out, like the second row. Okay, so let me try to zoom out here. And I drag this? No. All right, so while these first three, all work for relations that share the same schema, the rest of these result in something different. So here, the cross product relates in a schema that's more expanded. The projection results in a schema that is smaller in size, smaller in quantity. The select reduces the number of rows of the table. Rename changes the named attribute portion of the schema. And the natural join is sort of a combination of the cross product and the select. So all of these. See if I can zoom out here again. There you go. So all of these construct new tuples. Okay, and this is it. These 8, really 7, but 8 things, operations define what's available in relational algebra. Oh, my mic keeps blasting. Oh, I'm sorry about that. Maybe I'm just speaking too loud. I'll try to keep it with an inside voice. Or here, maybe I can. I don't know if this will do anything different. Okay, I've just plugged in some headphones. Okay. Okay. Still, I sometimes can speak too loudly when I'm teaching, so okay. So this is it. This is everything that is in the quote-unquote vocabulary of relational algebra. Let me create a page. So here, now we're going to go through examples. Before we go through, well, no, we'll just move on to examples. So the examples will take up the rest of today's lecture. Most likely, we'll just be going through more examples next lecture. These examples won't be too many, but each of them should demonstrate something concrete about sort of what can be done with relational algebra. So copy this relation. I really only need this part. I'll do these two. I'm not sure what is necessarily the way that I should have done that. Call this. And for now, I'm just going to put these sort of placeholders because I really don't care about the values of these. These questions are more about the schemas than they are about the values. So what kind of place do they frequent? All right, so we're going to focus on 4 relations. Okay. So here we have 4 relations. And I would like to know find all restaurants frequented by at least one person under the age of 18. Okay. So this is a question for you guys. You can take some time to think about it. But given these 4 relations, what is the relational algebra expression that would accomplish this. I'll write it here. So here's my question. What relational algebra expression results in answering this? I want to find all restaurants frequented by at least one person under the age of 18. I'll give everybody one more minute. If you come up with something, please type it in the text box, or after a minute, you can just say so through the mic. Okay, I see a few answers here. I also just got a good idea. I think the next time I do this, I'll try to get a timer app or something, or a timer, something to show a countdown. So this way, if you're rewatching this on YouTube, you're not just staring at a blank screen for 2 or 3 minutes. So you know how quickly to fast forward, but I'll do that next time. All right, I'll just start from the top. Person, X, frequents. All right, so I'm seeing people are using the natural join. I will, well, I'll just go through these one by one until we get closer to the end of class, and then if nobody's hit it, I'll just give the answer. So, person. If it's okay, Jamie, can you unmute your mic? Just because I want to make sure that I'm
Hi,
getting.
can you hear me?
Yes. Is this right so far? So do a cross product between these.
Yeah.
Okay. Then sigma less than 18. So you're saying this, like this.
Yes.
Okay.
So it would be age less
Then
than
pie
18.
restaurant. Okay. This is very close. Yes, this is very close. The issue with this would be no, that's not what I want. Well, just do it like this. So I can't get these to line up exactly, but let's say that I've glued together the tables like this. So this is what the cross product would do. Sort of glues these together. Of course, the number of rows would be larger. And the names under 18. So let's say, I don't know, just to give these some concrete values. John, who is 16, male, and I insert a new row here. And I'll say frequents say John, and he frequents I don't know, McDonald's. So what this would result in would be, boy, John, 16, male, Peter, 19, male, and okay. Okay. So it took a while to write out. Okay, so this so far is just this part. Okay, so taking each element in this and matching it with each element in frequence. So you have John 16 male being paired with John McDonald's, and Peter 19 male being paired with John McDonald's. Now you do a select of under 18. This would get rid of Peter, so that deletes this row. And, oh well, technically you do get the right answer here. And it would output McDonald's. So this does work for this example, but if I added, let's say, if I had another restaurant here, let's say here, if I put the name Mary here, then this again would be person times frequency. Sigma would delete this row, and pi would output this column. So it would output McDonald's. But John does not frequent McDonald's. So this is missing something. Any ideas, Jamie? No, Jamie, still there? Oh, okay. Mic isn't working, but no. Okay. So this is very close. In fact, I'll keep it to the side because this might be the thing to build off of. But that's a very, very good guess. Okay. Matthew, cross join person and frequent, then pi restaurant, sigma age under 18. Matthew, can you unmute your mic, or do you have a mic?
Hello, can you hear me?
Yes.
So yeah, I think I did the same thing as Jamie. I meant to say cross product.
Oh, cross product. Okay, great. Okay, thank you. Do you have? Okay, thank you. I'll go on to the next one here. Brian, pi restaurant sigma less than 18 person times frequency. Okay, so that's what we have already. Pi keep restaurants. Yes.
Can you hear me? I
Yes.
think in a couple comments below, I tried correcting mine, and I said if you do a natural join instead. And
Yes. Okay. So if you were to do a natural join instead, then well, let me see if I can just copy this whole thing over. Yes, thank you. So a natural join would work here. Let's see if I can just highlight everything here. That'd be great. Cool. Ooh, don't like that. Trying to get it on the same screen. Okay, so if this were a natural join, then it would result in an empty table because there are no values here in the name column that match the name column here, and choosing age under 18 and pi restaurant, this would output the correct thing. So yes, this here is correct with the natural join. Great. That is the way to do it with a natural join. Now I'm curious. I haven't read through all of these different comments here, but I'm curious if people know, because this answer here, without natural join. Does anybody have an idea how to fix this? What you could do to make this work correctly? If you have no idea, please say no. If you do, you can either type yes or unmute your mic. Yes, Jamie, you do have to make sure that the names match. So an if statement, Lydia, is not a part of our vocabulary. Again, this is the vocabulary that we're working with: union, intersection, set difference, cross product, projection, select, rename, and natural join. The thing that might be closest to an if would be the select, where you keep certain rows if some condition is met. But you might have to be more explicit by what you mean by using an if statement. Select through pi. Pi results in filtering columns. So yeah, you have to be very careful with words like using select through pi, because I don't know if you mean the relational algebra select or the English language select. What else am I seeing here? Would you nest the sigma age less than 18 inside of another sigma where name equals name? Tushar, you are on the right track. So Tushar says you could add another sigma, maybe here, sigma where name equals name. You actually, so you can do this. I mean, you can sort of repeat these sigmas over and over in this way. Another way of doing it that is a little bit cleaner is to just add an and. Name equals name. Okay. So this is closer still, but still missing something small. But this is where we're closer now. So where name equals name is what he's going at. But the thing is when you say name, how do you know if you're talking about this name or you're talking about this name? It's unclear. Both of them just have the word name. Person.name equals frequence.name. Tushar, yes, that is this. I'd take that as a correct answer, I guess. Yeah, this is that's more of a SQL way to, that would be one way to do it in SQL. But this is relational algebra. So there is no person.name. There's only name. Here, when you've taken these and sort of glued them together, this is not person.name, person.age, person.gender. And these relations don't have that exactly. Isn't it redundant that the names column are repeated twice? That's a hard question to answer. Yes and no. It's redundant, but this name column is, as Tushar is trying to point out, saying if this is frequency dot name and this is person dot name, this name column and this name column are different somehow, because this name column is coming from the frequency relation and this name column is coming from the person relation. So it's not exactly redundant because they're representing the names from two different relations. I guess you need pi. Yeah, still no pi. All right. So I will just say this because we only have one more minute of class. This here, this sigma, sort of doesn't compute because name equals name. It's unclear which name thing you're talking about here. So what you can do is you can change the name column here to something else. For example, name 2. And then here, now this column becomes name 2. And so this is the table for crossing these two together. So we took the frequency and we renamed one of the columns. Then you do a cross product to result in this table. Then you do a sigma to filter out not only when the age is too large, but also when name 1 doesn't match name 2, which then gets rid of this column, and you end up with the same table. So really, that is everything that the natural join does. It does a rename here. So it does a rename, it does a cross product, and then it adds a sigma to make sure that the entries in the columns are equal. Okay, so when you give answers later, I would prefer if you can do it in this way. I know it's a little bit longer, but this being explicit in this way can avoid some kind of hard to track nasty problems. So okay, that is it for today's lecture. If you need to get off, you can. I'll stay around for a little bit to answer questions if people have them. We can use the row function to rename the name 1 and name 2 based on their position. Yes, Eric. That's right. I'm sorry if you said that before I wrote it, then you nailed it. In the natural join table, the second name column doesn't go away. Oh, yes it does. Yes it does. Sorry. Yeah, this thank you. Could you quickly show what a cross product would look like if Frequency had 2 restaurants in it? Sure. So I will have, I don't know, Susan. She likes to eat at Henry's. Is that how you spell it? Or is there an E? I think it's just that way. Susan Henry's. Okay. So what that would look like is, let me give myself some more space here. John 16, male, Mary, and table. So the table would look like this. Let me see if I can move it up where you can see it all together. Right, so Anish. So what this does is, first of all, this would just be name. So if you were to take person cross frequents, then first it takes the schemas and glues them together. That's this part. And then it takes John and matches it to each pairing. So that's this row and this row. And it does the same for Peter. And that is this row and this row. If we repeated John and listed every restaurant, is it incorrect to list it that way? I'm not sure I understand the question. The order of these rows don't matter. So I could have this row, I could shift this row up. Sorry, it's not easy to do here, but you could rearrange the rows, but underneath the first row, just John 16 male, Susan Hendricks. Yes. So now let's see if I can, like this. There you go. Yeah, this works as well. These are equivalent relations. Yeah, there's nothing special about the order here. You can think of these as just a set of tuples. And for sets, order doesn't matter. And also there's no repeated elements, which is also the case in relations that you cannot have two identical rows. It will, yeah, each entire row at least needs to be unique. Mm-hmm.
I have a question.
Yeah.
So for the homework, question 3 is asking us to convert the ER diagram in question 2 into a relational model.
Yeah.
Do you just want us to do the tables itself, or do you want us to actually write, do it the other way, like writing it and typing it like the words and stuff.
Yeah,
Like for example, it's like create table,
right.
employees, and then do SSN, and then colon, and then characters, and
Right.
then
So, for example, for this ER
name.
diagram, would I want it like this, like a table, or would I want it written like this? Is that correct? That's what you're asking?
Yeah,
Yeah. I'm either
yeah.
way. Either way. I'll accept both. Yeah. You
Okay.
don't need to
And
give
we don't have to
both.
put any, like okay. Um. Okay, great. Can you help me a little bit more in question two, though? I'm like, it's like a lot's going on right now. Um. So for purchaser, can you like the dependents and beneficiary? So dependents is a weak entity, and beneficiary is the strong entity, or is it identifying entity?
So there is no strong entity. There's entities and weak entities.
Mhm.
Yeah. Um, and what was the other part of your question?
Um. So the arrows, is it the exactly one, or is it just like at most one arrow? Like I see it's bold, but is it the exactly one arrow, or is it the other one, the thin line?
Right. So
Just
there's
want to
there's a
clarify
difference
that.
between a thin arrow and a thick arrow. A thick arrow is actually just the combination of an arrow and a thick line. So a
Mm-hmm.
thick line says that there has to be at least one, and an arrow says that there is at most one. So a thick arrow
Yeah,
means
I understand that.
exactly one. Mhm.
I understand that, but is that the on the homework? Is it the thick one, or because
Yes,
is it the thicker one?
each of them are thick arrows. Yeah.
Okay, I just want to make sure.
Hmm.
Um. Okay. Okay. Cool. Thank you.
Sure.
Wait, what time is your office hours on Thursday?
Oh, I guess I'll start at 2 hours before class. So starting at
Before
say 3.
3. Okay. Okay. Cool. Yeah, because I still need a little bit more help on question two. So
Okay.
I'll ask you there.
Sure.
Okay.
Sounds
Thank you
good.
so much. All right.
Hmm.
Have a good day.
Yeah, you too.